let's do a canonical discriminant analysis using R. We're not going to try to classify any data sets or any unknown data in this exercise. I'm going to use the CanDisc package in order to do this, and at this moment that capability doesn't appear to be available. It is, however, available in the linear discriminant analysis, which you would run in essentially the same way that we're doing this one. Let's begin. Then we're going to clear the memory, and the next thing I'm going to do is simply put in the commands to choose the file. So let me just paste that right there. So I'm getting a data set which I'm calling NA-LIS, and I'm going to choose that from the data sets that I have here for experimental design. I'm limiting this to a CSV file that has just the North American desert lizards on it, not the Australian or Kalahari. I would recommend that you restrict yourself to one of those continents, not trying to do all three at once. So just simply go into the data file that you've already downloaded for the principal components analysis and delete the specimens that you don't want to use. Alright, so we've now got that data in there. Let's take a look and see what the data looks like. So view, and remember that when you use the view command, it's capitalized. So NA-LIS, I've called the data set NA-LIS for North American lizards, and it shows me the data set up here at the top. So you can see all the species, or the species, and they're numbered from 102 up to 133 or 134, something like that. I have two measurements here for jaw length. I have snout vent length, head height, head width, which might also be jaw width in the original data file, front upper leg, front lower leg, front foot, and so on. Okay. The next thing that we want to do here is look what the header looks like. So HEAD, NA-LIS, and that then gives us the top few rows. It's essentially the same information that we have in the table above. Now let's look at the structure of those data. So NA-LIS, so STR, NA-LIS. And as we look at this, we see that on here, species is an integer value, everything else are numbers. And we need to change that so that species, which is going to be our classification variable, will be treated as a factor. So we're going to have to make that change. Let's do that now. So here's NA-LIS, and I'm defining species, and I'm converting that to a factor using the as factor assignment. And then I tell it to use NA-LIS as the data set, and in particular the variable species. And now we can look at it again. So let's look at STR, and at this point it should tell us, yeah, so now species is listed as a factor. So very good. Now that's all set. Let's attach that data set. Okay, the data set is now attached. And what we need to do now is we need to call up a number of libraries that we're going to need in order to run this canonical discriminant analysis. There are a bunch of them. And you can type in the library command here, but if you're working in RStudio, it actually turns out to be easier just to go over here to this console window, which is hidden by me. Let me drag me down below. Whoops. Let's see if I can get me out of the way. There we go. Get me out of the way. Let's look for some packages in particular. The packages that I want to use are, let's see, I want CanDisc, so I'm going to click on CanDisc, and that right away then goes through this whole loading process. That should also load automatically the CAR package, which is essential. So that's companion for applied regression. What else do we need? Data table. We need that data.table. What else? I want this program here called mass. I want NNET. I want the psych package. I want rattle. And I want something called HE plots. I've already got HE plots there. I want ggplot2. We'll get that in there. Very good. I think we should be ready to go now. Okay, so now that we have that data set in there and we've got all of these packages in there, we've looked at the structure and so on, we should be ready to go. I'm going to use the command here which is called describe, and I'm simply going to describe my data set. Whoops. I don't know where the heck that's going. So describe. And I want to describe NA-Liz, but just in an effort to save space here, what I'm going to do is I'm just going to look at part of it, not all of the 13 variables or however many there are. And I don't need to look at my factor, I don't need to look at species, but I want to get a sense for what the distributions for these various variables are, like snout vent length and so on. So notice here I have describe paren NA-Liz, which is the name of my data set, and I'm going to specify now just some columns 2 through 5. Okay, so I just want to look at columns 2 through 5. Oops. And now what it's done is it's giving me the number of observations, the mean, standard deviation, median, the trimmed median, I've forgotten what MAD stands for, minimum, maximum range, skew, kurtosis, and standard error. So it's just looking at the first variables 2, 3, 4, and 5. Okay? All right. Now let's look at it in a slightly different way. I'm also going to describe it, but now what I want to do is I want to describe it on a by species basis. So I'm going to use the describe by command, and I'm specifying that I want to do this by species. And now I get this nice little table which shows me for each of these variables what the mean and so on. I believe the MAD is the median after the data have been trimmed. Okay. Next, now that we've described the data, what I want to do is look at it graphically, and I'm going to use that using this pairs panel command. So let's go down here. Let me type in the pairs panel command. So pairs panels NA-Liz, and I'm just going to ask it to look at variables 2 through 5, so not for species. And this actually produces a very nice result. If I do all of the variables, what I end up with is a display that's almost uninterpretable. But doing it just a few at a time, it produces a very nice little display. So here on the right hand side, let me take that and zoom in on that and then drag it over here so you can see it. And now you can see what's going on with these various data. So what we have here are scatter plots below the diagonal, and then we have a histogram which shows the basic distribution of the data, and then the correlation coefficients up above. So this column is snout vent length, and this row is snout vent length. This row is jaw length 1, and this column is jaw length 1. So here then, if I want to look at the relationship between jaw length 1 and jaw length 2, here's the scatter diagram for that, and here's the correlation coefficient. So you see that jaw length 1 and jaw length 2, these are two different measures of jaw length, and they're both highly correlated, and that's indicated by the correlation coefficient and also by the scatter diagram. Notice that head width is seems to be some sort of a bimodal distribution rather than a nice sort of bell-shaped curve, but that's fine. All right, so that's just a clever little trick to help you get a sense for where the collinearities are in your data set. All right, so now we want to set ourselves up to do the canonical discriminant analysis. And the way we're going to do that here is by essentially relying on a linear model that's generated through a multivariate analysis of variance. So here in this command, I'm defining a new model. I'm calling it model point 1, and I'm asking it to perform a MANOVA, which is just like an ANOVA, except that it's multivariate. And here, this cbind command, what I'm telling the R to do is to bind together these various columns. And the columns that I want it to use are snout band length, jaw length 1. I'm not using jaw length 2 because obviously over here I discovered that they're sort of redundant in the information that they contain. Head width, head height, and so on. And then I'm doing that, I'm creating this linear model by species. Remember that ANOVA and regression are both linear model techniques. The difference is in what you specify as the relationship between the factors. So here I'm doing that by species, and I'm telling it to use the NA-LIS data set. All right. So now there it's done the analysis, and what we want to do now is look at what it produces. So I'm going to use the summary command and summary model 1. And here it gives me the ANOVA table, right? And I have 21 degrees of freedom associated with species, so I have 22 species. 683 degrees of freedom associated with the errors. And notice it's giving me Pillai's trace, which is one of the statistical tests that we can use in a multivariate sense here. Notice too that for the denominator, or rather for the numerator degrees of freedom, I have 273. For the denominator degrees of freedom, it's 8879. Oftentimes, these denominator degrees of freedoms are estimated, so you don't get a nice integer, you get something else, okay? But regardless, it is highly significant. So I know that I have a difference between my species based on these variables. Well, that's sort of silly. I know that to be true. I mean, they are, after all, different species. All right, so now there's our summary of Model 1. Now let's take a slightly different approach to this. What I'm going to do is I'm going to create a new model, and I'm going to call this model.disc, so I want this to be the actual discriminant function. What I've done up above here with Model 1 is I've just done the multivariate analysis of variance. So let's do the discriminant analysis. So my new data set, model.disc, I'm asking it to do a canonical discriminant analysis of model 1, right? And I want it to do this analysis on the basis of species. Very good. So let's look at what the model is. So I'm going to type in model disc. And now it gives me some of the critical information that I need. So let's look at this table. It's giving me the canonical R squared for each. I have 13 canonical axes, right? So 13 canonical functions there. And the first one has an R square of 98%. And these are the eigenvalues. So the sum of all the eigenvalues, 50 divided by the sum of all these eigenvalues, then is going to give you the percent of variation that's contained on that particular axis. So here you can see that the first canonical function accounts for 50.6% of the variation amongst the data points or amongst the groups, and it gives here the cumulative value as well. So the second one is 21%, the third one is 11%. Notice that these are monotonically decreasing. So if I restrict myself just to the first two axes, I'm explaining almost 75% of the variation in this data set, which is pretty good. Okay. And notice here I get my test results down here, the approximate F's, the numerator degrees of freedom, and here you'll notice the denominator degrees of freedom. You get these decimal values rather than these nice integers. Okay, so that's just a consequence of the way degrees of freedom are estimated in Hotelling's trace and Wilks lambda and all those sorts of statistical tests. Very good. So now we have this, we've looked at model disk. Let's get a summary of that. So type in summary. And part of what it's going to give us here is just exactly what we've had before. But in addition to that, so now here's this table we had from up above. But notice now that it's giving us across 3 dimensions, so the first 3 canonical discriminant functions, it's giving us the class means for each species. So if you're doing a project of this sort and you want to plot where these species are in canonical space, these are the coordinates that you would use, right? So you could plot these out in a scatter diagram, 1 versus 2 or something like that, and then discover what the relationships amongst the species are. And then here we get the standardized coefficients for each canonical function. So canonical function 1 here, notice that these are no longer correlation coefficients, right? Because you can't have a correlation that's stronger than 1. But these are standardized, so because some of these numbers have very much smaller ranges than other numbers, we're not going to get this nice sort of pattern that we saw when we were doing the principal components analysis. All right, so what have we done there? That was our summary of model disk. Very good. Now let's look at the structure. So we're going to type in model.disk. And then I'm going to use $ structure. And now we get the canonical structure for not just the first 3, but for all 13 of our variates. Let's now look at model disk coefficients. And standardized, and that gives, whoops, what did I do? I can't spell. So model.disk coefficients, and I want the standardized ones first, and that's for all of the axes. We just had the first 3 before. Now we get them all, or we can look at the coefficients raw. So these are not standardized, and you'll see that the values now are much more difficult to interpret because, of course, they're not all our observations are not standardized. Okay. All right. What we want to do now is look at this in a slightly different context. We're going to use the HEplot package. And we're going to perform the HEplot for model.disk. Whoops. Modella, right, okay, so again, I can't spell HEplot. There we go, and now you see this, this nice little graph over here on the side. Let me make sure that's perfectly available to you. Let me zoom if I can. All right, and let me move it up. Well, you can't see the bottom of it, but you'll get the idea of what this sort of graph looks like. So the x-axis is canonical axis 1, the y-axis is canonical axis 2. And here, canonical axis 1 explains 50.6% of the variance in the data, and then canonical axis 2 explains 21.4%. And this is also giving me something that's referred to as a biplot. So you can see what's happening along canonical axis 1 and 2. So for example, snout vent length is this vector going down in this direction. So as we go in this direction, we're finding animals that are longer and longer, and as we go in this direction, animals that are shorter and shorter. In this direction up here, you get animals with longer rear feet, and in this direction, animals with shorter rear feet, and so on. Body weight, or body width rather, animals over here on this end of canonical axis 1 have wide bodies, and the ones over here have skinny bodies. So this gives you a nice way of sort of getting a sense for what's happening to these lizards morphologically. Obviously, if you were doing some sort of a study on behavior or something of that sort, this might have a different interpretation. Okay, now let's do this. Let's make model 2. And what I'm going to do, for model 2, I'm going to do my can disk of model 1 and data equals NA-Liz. And now what I'm going to do is I'm going to add this little command back here. So ndim equals 1. So number of dimensions is simply 1. Okay. So now I've basically just done the canonical discriminant analysis all over again, but I've done it simply so that I can perform this plot. So plot model 0.2. And now you get a, let's see if I can zoom this thing. It's not showing up for some reason, but that's fine. Along the x-axis here we have species. I know you can't see it, but each column here is labeled species. So from species number 1002 to species 1033. These are box plots, and these are the box plots for the position of that species along this first canonical axis. And you notice these open circles, those are outliers, right? So there are some observations that are extreme. Those are probably juvenile animals or something of that sort. But overall, for many of these species, the distributions seem to be nice, reasonably symmetric, so it gives you a sense that there is some normality in this data set. And over here in the right panel, you see all of the different variables and the directions and magnitudes for those variables along this first canonical axis. So here, for example, snout vent length, longer animals are down at the bottom and shorter animals are up at the top. And that runs opposite, for example, to digit 4, the rear foot, which seems to be one of the large variables along this first canonical axis, and it goes opposite to body width, which is this vector on the far right-hand side. So this is just a nice way of presenting the data and finding out which groups are different and in what ways are they different. You notice that there tend to be a couple of groups, right? There's this group of animals right here, a group of animals right here, and then this group of animals down here. It turns out that these guys down here are the phrynosomatid lizards. Those are the horned toads. And these guys up here tend to be the nematophorine or the teid lizards, so the race runners and things of that sort. So there it is, a nice introduction to canonical discriminant analysis. And again, if you want to use this in order to classify unknown observations, Instead of using CanDisk, use the LDA function, and that's available on under the packages as well. When you go to the right and look at packages, you can find it. And that then allows you to classify observations. Okay, that simply at this point is not available in CanDisk, or at least I've not been able to find it. Very good. See you guys next time.